Good afternoon and welcome to Year 2 Trigonometry Lesson 1. This lesson is all about small angle approximations for trigonometrical functions. A little bit of a recap to begin with. I'm going to give you two. Here's one. I'm going to give you two questions all about radians. Can you have a go at this question, please? And your answers are: the value of theta is 1.2. and the length of the arc is 7.2. Next one, can you have a go at this question, please? Here's the answers. Your sketch of the graph of y equals cosx. It crosses the x-axis at pi over 2 and 3 pi over 2, and it goes on the y-axis between 1 and minus 1. The end of the sketch, it can go beyond, but it must go at least until 2 pi. For our equation, it's using that trig identity, sine squared plus cos squared equals 1, and marking that out there, doing the algebra on it, and we do in fact get to the cos theta equals a half. Hence solve the equation. So having realised that's the case, you're now looking at what's similar and what's different between the two equations. I can see that theta is being replaced out with 2x, but otherwise they're exactly the same. So in fact, what I'm going to solve for this part 2 down here, I'm going to solve that cos of 2x equals a half. What I am going to be careful to do is, because I've got 2x there, I'm going to double the range. So I'm going to think about all of the angles in between 0 and 2 pi. So that gives us, in decimals, 0.524 or 2.62, but in fractions it comes out nicer because you've got pi over 6 or 5 pi over 6. So what we've got here is our graph of y equals sine x. Nothing special going on here. It's a regular old sine x graph. The question could be, though, what is the gradient at any point on the sine x graph? Well, I guess at the maximums and minimums, I can see the gradient here will be 0, the gradient here is going to be 0, the gradient here is going to be 0, and so on. At this point here, it looks like it's really quite steep, though. But that's an illusion, and it's an illusion because in fact, the x-axis has been really quite squashed up. We've got 90 units going across here in this first box, whilst we've only got a half or even 1 going up on the y-axis. So what we can do is we can square this up. And when we square it up, you can see I've got squares now. It looks like if we're going to measure sine x in degrees, then in fact the gradient for this section of the graph here is really quite low indeed. Now that's where radians comes along and does a much better job of this, because if I switch to radians, then the gradient works out a lot better. I can see that when x equals 0, looks to me that for every unit I go across, I go up 1. Looks to me that the gradient there is 1. Okay, up here, as I mentioned, the gradient here is 0. Here, for every unit I go across, every unit I go down, I go across 1. So the gradient here is minus 1, and just to note that that point there will be pi. Okay, so that value there is for when x is equal to pi. Okay, I didn't mention this is pi over 2 here. This one over here, the gradient again is 0, is going to be 3 pi over 2, and when we get to 2 pi, the gradient again is 1. Now I could carry on doing that, and it looks like these things might be forming some sort of a pattern, and in fact they are, because if I plot this one, y equals the gradient of y equals sine x gives us the graph of y equals cos x, and then we can repeat this. So this time, what if we differentiate cos x? Well, the gradient here is 0, so I'm going to try and mark that on. So there I am marking that one on as 0. At this point, the gradient is minus 1. At this point, the gradient is back to 0 again. At this point here, the gradient is 1, and at this point here, the gradient is 0 again. So what happens if we join up these points here? Well, it turns out that if we differentiate y equals cos x, we get y equals minus sine x. Now then, we're going to do something slightly different. We're going to look at a particular section of each of these graphs. Okay, so I'm going to square this up again, and I'm going to do it in radians again, and I'm going to look at what about if the angle is really quite small indeed. And look at that, our graph suddenly appears to be very, very similar to the straight line y equals x. You can see it does taper off a little bit at the ends there, but for when the angle is really, really small, then the graph of sine x can be approximated by the graph of y equals x. Now, similarly, if we repeat that for tan, let's see what happens here. So I'm going to put it to radians, and I'm going to square it up. That's better. And I'm going to look in at when the angle's really, really small. And again, we can see that we just got that straight line. So it turns out that, well, it doesn't do quite such a good job, but it's pretty similar all the same. For small angles, then tan x can be approximated by the line y equals x. So what about cosx then? Let's take a look. So here's our cosx graph, sticking it into degrees, sticking it into radians and squaring it up. And if we zoom in here, well, this doesn't look quite so easy. Let's take a look. So zooming in here, what happens here? Oh, well, doesn't look quite so easy. It certainly isn't the y equals x line. Looks like it could be y equals x squared. However, y equals x squared is that way up. Well, you know what? We can sort of change that. Looks like, let's try y equals minus x squared. Well, that's all right, except it goes through 0, 0. So we'd better lift it up a little bit. So let's add 1 on the front there. Well, that's not so bad. I think we need to do one more thing. We need to stretch this out. Put a factor of divide by a into there. Now let's see what happens when we manipulate that value of a. If I stretch that out, then it seems that, you know what, I think that'll probably do there. So for small angles, I'm going to zoom in so we can see those small angles, sort of between x equals minus 0.4 and 0.4, then the graph of 1 minus x squared divided by 2 will approximate the cosx graph. The text at the top there is what you get given in the formula book, so you don't need to remember these things. I've broken it down so you can see each of them separately a bit clearer on the left-hand side there. So the sine theta graph can be approximated by a graph of y equals theta. Same for tan theta, y equals theta. Cos theta can be approximated by the graph of 1 minus half of theta squared. Okay, for the sine one, you replace sine of whatever it is with whatever it is. For the tan one, you replace tan of whatever it is with whatever it is. For the cos one, you're going to replace cos of whatever it is with 1 minus half of whatever it is squared. Can you write those down, please? Can you have a go at these questions, please? So your answers here. Sine of 2 theta will become 2 theta. Tan of 3 theta will just become 3 theta. Sine theta cos theta will become theta multiplied by 1 minus a half theta squared. And if you multiply all that out, you're going to get theta minus a half theta cubed. The next one, tan theta times by cos 2 theta. So the tan theta gets replaced with a theta. The cos 2 theta gets replaced with a 1 minus half 2 theta all squared. When you multiply this out, just be careful that 2 theta all squared is 4 theta squared. And you're going to do more multiplying out, and you get to theta minus 2 theta cubed. For the last one, 1 minus cos of 2 theta. So you're going to replace the cos 2 theta with a 1 minus a half of 2 theta all squared. That gives you 1 minus 1 from there, plus a half times 4 theta squared, which comes all the way down to 2 theta squared. Excellent. Can you look at these questions, please? So your answers this time. Replacing things out, the 3 cosx becomes 3 lots of 1 minus a half x squared, and the sine 2x becomes 2x. So that gives us a quadratic, which you can stick in the calculator or you can solve, and we get a root of 0.39. The second one, so the tan x gets replaced with an x, the sine x gets replaced with the x, cos x gets replaced with 1 minus half x squared. When we multiply all that out, do stuff on it, the smaller root is 0.204. Okay, what about if you get questions like this? Can you ever get this one then, please? So you go from the top equation to the bottom one by replacing your stuff out. You replace sine of whatever it is with whatever it is, tan of whatever it is with whatever it is, the cos one gets replaced like that. Then do the algebra, which becomes that algebra there. I'm not going to read it through to you. You can pause the video and check that through for yourself. But you can see it does get the right answer. Next one. Same thing, please. Can you repeat and do the same as what you just did? There's your rules again. And your answer is, again, I won't read it out to you. In fact, there's a bit of a bodge here, I think. This theta being small, implying that theta to the power of 4 is 0, so that last term kind of drops out. There is a better way. Here's an alternate version using maths that you'll learn in trigonometry lesson 6 in 2 or 3 weeks' time. In trig lesson 6, you'll get to the identity that cos squared theta is equal to a half plus a half cos 2 theta. There's a cos 2 theta there. So what I've done here is to replace out that cos squared theta with this identity here. That's the blue stuff, okay? Multiplying out, replacing my cos theta and my cos 2 theta with the stuff in green. That's swapping out for the small angle approximations. 1 plus 1 is the 2 there. There's another constant term, so that's the yellows are my constant terms. Multiplying out the brackets on the end here, and then doing some more stuff on it, it does in fact come down to the answer we were hoping for. I'll let you read that through in your own time. Next question. Can we use small angle approximations to help us to solve this one, please? This one here does say that we're allowed to neglect the terms in theta cubed or above. So I'm going to use that first version that we just did, when we're just going to ignore anything that we get theta cubed or above. There's your rules again. And the answer for this one gives us these things here. For this one, the small angle, we know that theta is going to be small, so we're going to ignore the -6 answer, and the one we're going to use will be the 0.206. Okay. Okay, this time, so this gets interesting. Can we differentiate y equals cosx from first principles using the identity which we will learn in trig lesson 5? I'll go through this one with you, so follow the steps along, please. So, differentiate from first principles. It's the difference in the y values divided by the difference in the x values. The second y value will be cos of x plus h. The first y value will be cos of x. The second x value is x plus h. The first one was x. Now then, that's where we're going to pop in our identity. So our identity, the blue stuff, is slipping in there. And at the same time, I've cancelled out the x's on the denominator. Now then, I've then done some factorising. So cos x, how many cos x's have we got? Well, we've got cos x times cos h minus another lot of cos x. So I've got cos x times by cos h minus 1. That's all divided by h. And I've also then got this sin x times sin h which is also divided by h. And here's the clever bit. For small angles of h, the easier term to do, the sine one, sine x sine h divided by h, well, the sine h we can just replace with an h, and then those h's cancel. So that sine term just drops all the way down to a sine x term. For the cos term, cos h, if h is small, that gets replaced with a 1 minus a half h squared. And when we do the algebra on that, we get down to minus a half h squared cos h. The h's cancel, and so we get down to that version there. So our equation becomes the purple bit, or the pink bit you can see here, minus a half h cos x minus sine x. And then we can say that as h tends to 0, this cos term is going to disappear, and we get left with minus sine x. So we've just shown from first principles that the cos x graph does in fact differentiate to be the minus sine x graph. And there we go. Your task, can you repeat that for the sine x graph? And I've given you the identity that you're going to need there. We looked briefly in this earlier on in the term, and we'll go into a bit more depth on it this time. So hopefully a bit of a reminder. We've got sec, cosec and cot. All we do here is redefine or rename 1 over sine as cosec, 1 over cos as sec, and 1 over tan as cot. As we proceed through, what you'll see is that every time we see each of that cosec, sec or cot, we just substitute it back out with the respective 1 over whatever it is. There is a quick and nice easy way to remember these. You look at the third letter of each of those words. S in there, cosec, S for sine. Sec, we get C for cos. Cot, we get T for tan. One important thing to note here, down on the left-hand side of the screen, is that sine to the minus 1 does not mean 1 over sine theta. It does not mean cosec theta. For trig, that notation means the inverse function. Your first task would be, or could be, can you please sketch each of the graphs on the same axis as its reciprocal function? We're going to do it between minus 4 pi and all the way up to 4 pi. You could use this pre-drawn graph here to help you. You might want to pause the video at this point and download that. I'm going to use some software to help me do it. So I moved across to the software, and I've got an image of sine, I've done it in radians, cos, done it in radians, and tan, I've done it in radians. You might well be thinking, but sir, they're really short. Why have you done them so short? Well, we will see. So we're going to try and plot the graph of 1 over sine x. Well, where are we going to start? Well, what do we know? When x is pi over 2, then sine of that is 1. If we do 1 over 1, we in fact get the same thing there. Okay, I reckon probably around about there is a value of a half. So if we do 1 over a half, 1 divided by a half, then that gives us the value of 2. And not only that, but probably somewhere over there, there is also 1 over a half, which gives us the value 2. Hang on, I can do better than that, because I think I've also got half there minus half, so that's going to give me minus 2, and similarly I can do that one there. Why stop there, you say? Because you could do a third. Yeah, you'd be right, that would give you 3. You could do a third there, again you'd be right, that would give you 3 as well. What about a quarter? Well, that'd give you 4. What about a quarter? Well, that'd give you 4, and so on. What about 0? 1 divided by 0? Oh yeah, not allowed to do that. That would give us infinity somewhere up there and somewhere up there. What about when we come from the other side? If we come from negative, yeah, right, that would give us minus infinity, and we'd probably get minus infinity there. Hold on a second. So does that mean we'll get positive infinity there and there as well? And then minus infinity again over here, coming down to 1 again over here, coming down to, sorry, minus 1 over there, 1 over here, and so on. What about this area in between here? Well, what's this going to be? This is going to be like 2/3 So that would give us 1 divided by 2/3 would be 3/2, which is 1.5. It fits nicely in there, doesn't it? Hang on a second, I think I've got the hang of this. This gives us a lovely smooth curve there. And I'm sure you can see where we're going with this one. We're going to get a lovely smooth curve, whoopsie, down there. I can do better than that. Let's get the graph the computer's plotted. Y equals 1 divided by, put it in brackets just in case, sine x. There you go. So that is in fact what it should look like. There's our graph of cosec x. I'll delete the wrong bit. There's our graph of cosec x. So if I now go through and get rid of my scribbles, such that they are, there's our graph of cosec x. We can do a similar thing. You know what? I'm going to skip out all of the scribbling stage. Y equals 1 divided by, excuse me, cos x. That gives us that graph there. Tan x is a little bit different. Let's think about that one again. As ever, tan's busy doing its own thing. Right then, 1 divided by 1, that's going to give us that point there. 1 divided by a half, that's going to give us a value of 2 there. All right then, 1 divided by 2 is going to give us a half. 1 divided by 3 is going to give us a third. 1 divided by 4 is going to give us a quarter. 1 divided by infinity is going to give us 0. Hold on a second, this bit's symmetrical, isn't it? And it's going to come across there. So we're going to get some sort of a curve going out to there. What's it doing here? Oh yeah, this is 1 divided by a third is 3, 1 divided by 4 is a quarter, and so on. So we're going to get this type of curve going down like this. And what's going to happen? It's going to repeat, isn't it? Of course it is. So it's going to come down, cross at 1 again, come over there, whoop, crossing at 0, excuse me, cross at 1 again, and get on down to infinity. Okay, so the y equals cot x, or 1 over tan x, gives us a graph looking something like that. So there's your graph of that. So there's our graphs of y equals, which one's that? Y equals cosec, y equals sec, and y equals cot. Fantastic. If you want to, you can download nice printable copies of these graphs at that website there. I'll let you pause the video while you download those. I don't think you're really going to be asked about those on exam day. On a bad day, you might be able to sketch them. You've then got the option of remembering them or plotting them out like I showed you there. The main part of this is going to be dealing with trig equations where we've got sec, cosec, and so on involved. I've been nice to you, giving you 1, 2, 3, 4, 5 questions involving degrees, and then there's 5 questions involving radians. You will also spot that I've also been nice and given you very similar equations there. As I said, first step, you're going to take that. So, for example, for A, you're going to replace that sec x straight away with a 1 over cos x equals 2. Excuse me, and manipulate it from there. Can you have a go at those questions, please? And your answers are, for the first set, so A was 1 over cos x equals 2. That rearranges to cos x equals a half, and so you get the values 60 and 300. For part B, it's 1 over cos 2x, so don't forget to double the range, and then half all your values afterwards. That gives us x values of 30, 150, 210, 330. Part C is cos x, so you're going to do 1 over sine of x over 2. That just gives you one value of x equals 180. Part D, a little bit of rearranging here because you've got two things. You've got 3 over cos x equals 10 over sine x. Multiplying through both sides by sine and cos, multiplying through by sine x and dividing through by 3 will get you to sine x over cos x, which is in fact tan x, equals 10 thirds, which solving that gives us the values of x equals 73 and 153. For part E, you're going to replace out sec squared with cos squared. You're going to replace out sec with cos x. That's going to give you that. You're going to multiply up to get there, and then you're going to be busy factorizing. You'll notice that one of them, cos x equals minus 2, gives you no solutions. I do advise writing that down. Don't just ignore it and pretend like you didn't realise it, but write that one down and then write down that there are no solutions here. Even better is if you can say why there are no solutions, something along the lines of that the cosx graph only goes between -1 and 1, or it doesn't go down as far as -2. So you have got some solutions from the other one. Cosx equals a third, so x is going to be 70.5 or 289.5. Your second set of answers are those ones there. I won't read them out to you. I'll just let you pause the video and look at them yourselves. Right then, can you remember those things there? Sine squared plus cos squared equals 1. We can do some stuff on that. If we divide through by cos squared, that gets us to this equation here. And then we can spot that sine squared over cos squared is tan squared. Cos squared over cos squared is 1. And 1 over cos squared is then cosec squared. Similarly, dividing through by sine squared, that gets us to that situation there where we get 1 plus cot squared equals sec squared. Can you pause the video and write those ones down, please? Now we're getting into it a little bit more. Can we prove that the left-hand side of that top equation does in fact equal the right-hand side of the top equation? On the right-hand side there, you've got that x is not allowed to be any kind of multiple of pi divided by 2. That's just a clarifier, because if x is any of those values, then it makes the denominator 0, and we're not allowed to divide by 0. So let's have a look. What would we do to get from there to there? Can you have a go at this? And then when you're ready, I will show you what I did. So here's what I did, or here's what the mark scheme says even. Quite a nice one, this one. So tan x is sine x over cos x. Sec x is 1 over cos x. Nothing to do on the denominator, I wouldn't bother doing that bit. You can multiply through and then do some cancelling, and it does in fact simplify down to be -1 over cos x. All very nice. So having done that, can we solve the following equation? So we're not going to solve that equation, are we? We're going to solve minus sec x equals √2. So minus sec x equals √2. In that case, we can manipulate that so that it's cos x equals -1 over √2. You can rationalize denominator if you want, or in any case, you're going to solve it, and you're going to get to that x is equal to 3 pi over 4 or 5 pi over 4 in that interval there. Very good. Right, next one. Can we show that that top equation can be written in the format of the next one down, where you're going to find out what A, B, and C are? Can you have a go at everything on this page, please? And then I will lead you through it. The algebra for the first part. We replace tan x with sine over cos. We replace cot x with cos over sine this time. You could go for 1 over tan, but I think the next step would be to replace out that tan with a cos over sine anyway. And the 5 cosec becomes 5 over sine x. Doing some multiplying through by cos x and by sine x gets you to the third line down there. 2 sine squared minus cos squared equals 5 cos. Doing some rearranging and some factorizing and some expanding then gets us all the way there, and we find out that A is equal to 3, B is equal to 5, and C is equal to -2. Hence, can we please solve that equation that was given at the top? But we're not going to solve that one. We're going to solve that one, that quadratic that we just found. And our first step to doing that is to factorize it. And we find out that cos x can be -2, which leaves us to no solutions, or cos x equals a third, which leaves us to those values there. It does feel very similar to that question E from a few slides ago. Okay, another type of question. What about graph transformations? Can we describe a sequence of 2 geometrical transformations that maps the graph of y equals sec x onto the other one? Now, you may be able to do this without even involving those identities and rewriting it. Okay, so I've chosen to rewrite it. So sec x is 1 over cos x. 1 plus sec 3x is 1 over cos 3x plus 1. I have moved the plus 1 to the end just so it's clearer for me to understand what's going on. So what have we got? We've got a 3 down there tucked in with the x. So because it's all tucked in there, part of the thing down there, It's a horizontal, it's multiplying it, so it's a stretch, and the scale factor is a third, because it does the opposite when you're doing horizontals. The +1 is translating it upwards by 1 unit. Well, you could just say translate by 0, 1. Those are your transformations. Next one, can you have a go at this question, please? Show that the following equation can be written in this format where it's equal to 16. From what I remember, this one is particularly difficult. We'll just work it on through and see where you get to. So the maths on this one, multiplied through the whole thing by 1 plus cos theta and also multiplied through by 1 minus cos theta. That gives us the stuff we've got on the left-hand side, and there's those two factors being multiplied up on the right-hand side. I've realised that the minus cos and the plus cos cancel on the left-hand side, and the 1 plus 1 equals 2. And on the right-hand side, I've expanded those out and realised that it's a difference of 2 squares. So that gives me to that one. So we get 2 equals 32, 1 minus cos squared theta. And then, of course, 1 minus cos squared is equal to sine squared. And we can also divide by 2. So that gets us 1 over 16. Sorry, 1 equals 16 sine squared. We can then divide by sine squared. And that's where the cosec squared comes from. So cosec squared does, in fact, equal 16. That is tricky, so it's worth having another go at that on your own if you didn't get it the first time round. Hence, solve the equation. Well, we're not going to solve that one. We're going to solve the other one that we've got. But these are different, aren't they? Because in the first time we had a theta, and in the second equation, we've got 2x minus 0.6. So I think it's going to become, where are we going to go from? We're going to go from 1 over sine squared of 2x minus 0.6 equals 16. Okay, multiplying up, dividing down gets us that sine squared of 2x minus 0.6 is 1/16. Square root both sides, and importantly, remember that you can take the plus or minus of a quarter. And then we've got the transformations from 2x minus 0.6 into x values right at the end there. We get 0. So the x values are 0.17, 0.43, 1.74, 2.00. And this is our final thing here. One last thing. You may have already realised this. From here on onwards in your mathematical career, unless indicated otherwise, always assume that anything involving trig is in radians and always work in radians. Because, sure, 360 is a nicer rounder number, and when you're in high school and when we did all the stuff in degrees, it just makes a bit more sense. We can get more of a feel for it, but radians make the maths make sense. Otherwise, as you saw with the differentiation and the gradients and so on. Thank you very much.